Hi everyone, I'm Matt from ceramicmaterialsworkshop.com, and I'm here today with another video in our series, Everything You Want to Know About Clay and Glazes, but Didn't Know Who to Ask. And today's question is, how do we calculate the UMF, the Unity Molecular Formula? Now I'm going to start with a caveat. This is a little bit more of an advanced talk. So if you're a newbie, I encourage you to watch the video, but you're going to be scratching your head. And if you want to know more, please stop by ceramicmaterialsworkshop.com and take part in our online workshop, Glazed and Confused, Understanding the UMF, and it'll fill you in on all of this information. But if you're a more ceramicist, you're going to know where we're going with this, with calculating the UMF by hand. Now, at the end of the day, I actually don't encourage you to do this by hand. There are a glaze calculator on ceramicmaterialsworkshop.com that works in Microsoft Excel that's absolutely free, and I encourage you to take it. Or there are websites like glazy.org, which is an amazing resource for cataloging and documenting your glazes, and it has a built-in UMF calculator, and it works beautifully. But if you're trying to understand the UMF, you should do the calculations a few times by hand to understand where the numbers are coming from. So that's what we're going to do today. So let's start. The first thing we need is a glaze formula, and we're going to start with the old standby 4321. It's a very simple cone 10 glossy glaze, and it works great every time. Now, there's a lot of variations in the formula of 4321, but this is my favorite version of it, which is 40% nepheline cyanite, 30% flint, 20% whiting, and 10% EPK. So let's run those UMF numbers and see how this works. First, we need to do some background, okay? We need to go into our procedures, and we're going to need two pieces of reference material. The first is we're going to need the molecular weight of our ceramic oxides. That's materials like silica, alumina, sodium, potassium, magnesium, calcium, iron, and titanium, and there's a few others that we're not using in this recipe, but will come up in other glazes. And the thing about these is that they never change. So you can write these down, make a note in your phone, tattoo them on the back of your eyelids, because they'll always be the same and you'll always need them. Silica is always 60.09, alumina is always 101.96, etc. The second thing we're going to need for our formulas is we're going to need the chemical analysis for our raw materials. And there are several places online where you can find the chemical analysis for our raw materials. My particular favorite is to go again to glazy.org/materials/glazy. And in there, you'll find a list of all the ceramic raw materials that we use commonly, and Glazy is great because it's got American materials and international materials. It's a wonderful resource. So all you need to do is find the name of your material, and we're going to start with just EPK here. And all we're doing is pulling out these numbers. And what this is telling us is how much of the individual components of the material are in that material. So silica is 45.73, alumina is 37.36 down the line. And we need to collect these numbers for each of the materials in our glaze. So in this case, we'll need nephi and flint and whiting and EPK. But we're not going to do each of those. We're just going to jump ahead. So now the procedure for actually calculating the UMF. I'm just going to read these off, and you're going to be very confused. And again, once we're done the video, I encourage you to come back and it will start to make more sense, but we need to document this as we proceed. So, step 1, multiply the ingredient components by the formula. Step 2, add together the oxides from each material. Step 3, convert to moles, which is weight divided by molecular weight. Step 4, sum the fluxes. Add all of the fluxes together, and that includes lithium, sodium, potassium, magnesium, calcium, strontium, barium, and zinc. Finally, divide each molecule by the sum of the fluxes, and that gives you the UMF. Now, I'm sure you're saying at this point, Matt, what on earth are you talking about? This is crazy gibberish. Those aren't even words and sentences. But let's proceed, and I think you'll start to see it a little bit more clearly. So the next thing we need to do is we need to make a chart. Now, this particular chart is the way I would lay it out, and I've got 10 columns and 15 rows. And it's pretty simple of what you need. You are going to need 2 rows per ingredient. So here's nepheline cyanite, and it's got 2 rows. You're also going to need 5 rows at the bottom. The sum of the oxides, the molecular weight, the moles, the sum of the fluxes, and finally our UMF results line. So I've got a few in here extra. I've got redundant listings of what our oxides are to keep track of stuff, but in general, this is a pretty good grid. So for a 4-ingredient glaze, again, I'm 10 by 15, but this varies depending on what your formula is. So the next thing we need to do is we need to insert our chemical analysis and the formula. I've already done this, again, pulling the formula from glaze.org or other resources. So here is, again, that chemical analysis transcribed into the individual lines. And I've got NEFSI, then whiting, and flint, and EPK, and I've inserted the formula 40, 20, 30, 10. Now you might notice I switched the flint and the whiting, and that's because it's normal glaze nomenclature to keep our fluxes together. And in this case, it just doesn't work with the numerical remembering of 4, 3, 2, 1, because we actually have 20% whiting. It doesn't make a difference at the end of the day. Okay, so now we've got our grid laid out and we need to start the calculations. So how do we do it? The first step is we need to multiply the ingredient components by the formula. Okay, and the math here is pretty simple. We take that chemical analysis number that we got. So for nepheline cyanide, it's 61.95% silica. And we have 40% NEFSI in our recipe. So we don't want 100% NEFSI, we want 40% NEFSI. And to get that number, we just move the decimal place on our 40 over 2. So we go 2, and we equal 0.4. So the math is pretty simple. 61.95 multiplied by 0.4, and you do that and you get 24.78. Makes sense? Okay, let's try alumina. Alumina is 22.1, again, multiplied by 0.4, and you get 8.84. We continue down the line for each and every component. Sodium is 10.29, multiplied by 0.4, and we get 4.12. This makes sense to everybody? So again, the 40% component is just what this recipe happens to have. If your glaze is 56.3, okay, you're going to have 0.563. It's the same moving the decimal point, okay? Just happens we're working with the nice round numbers because it makes the math slightly more simple. But we're going to go ahead and finish off each individual component at once. So here's the rest of the glaze again, multiplying each component by the amount of the material in the glaze with that moved decimal point. So here are all the individual components and we've written them down. So now nepheline cyanide is done. We move on to whiting. Okay, whiting is a great material because it's only got one relevant oxide. That's calcium oxide at 56.3%. Now you might be saying to me, Matt, but why isn't it 100%? You know, whiting is calcium carbonate. Well, the part that we're missing is the carbonate. That represents carbon dioxide. And that carbon dioxide gets driven off early in the firing and doesn't play any ceramic role, and so we don't account for it. But the important part is that 56.3% of that whiting is the actual calcium that we need. And we have 20% whiting in our glaze, so the math again is simple. 56.03 times 0.2. Again, we're using the individual component, equals 11.21. And now we're done with whiting because there's no silica, there's no iron, there's no sodium in our whiting. It's just calcium, so we're done. So we move on to flint. Now, flint is primarily silica. In fact, it's 98.54% silica. So we multiply 98.54% silica and we get 29.56. Okay, now in silica, there are other trace elements, and we're going to go ahead and do the math on those. But they're very small, but we want to account for as much as possible. Okay, so we're going to fill out the rest of these numbers. The one thing I will say is talking about significant figures. When we're calculating by hand, I like to go to 3 significant figures. That's 3 numbers past the decimal point. If the numbers are any smaller than that, I will discard them when doing the math by hand because they're really small and don't play much of a role. Now, if you're using a piece of software, the great thing is that they don't ever have to discard them. The numbers can be infinitesimally small and they'll be compensated for. So this sometimes leads to a discrepancy between numbers calculated by hand versus numbers done by a spreadsheet or by software, but that's okay. We often find a lot of variation in UMF numbers, especially because you could be using different chemical analysis reference. If they run a sample on a different day, the analysis is slightly different. So you're going to find small variations, and that's all right. You just don't want to see any major variations in your UMF numbers. So these all have 3 significant figures, so we're going to keep all these numbers. We're then going to go down to EPK, okay, which again is 10% of the formula, so 49.44 times 0.1 equals 4.94. 35.46 equals 3.55, so on and so forth down the line. Okay, makes sense. So now we've got the percentage of each of the individual oxides in each of the materials. Okay, so now we're going to keep going and we're going to go to the next step, which is sum the oxides. And what that means is we're going to take all the silica from all of our sources and we're going to add it together. Because the cool thing about glazes is that they do not care where the raw material comes from. Silica is silica is silica in our glaze. So if it comes from nephsi or it comes from flint or it comes from clay, it's all the same thing because in the glaze, everything melts. Okay, it all becomes part of the soup, so any silica number is relevant. The only place where this is really not true is if you're using raw forms of alumina, alumina oxide and alumina hydrate. They do not melt. You can only get alumina coming from other materials like nepheline cyanide or feldspars or clay. So we're going to take all of the silica. So we've got 24.78% from our nephsi and 29.56% from our flint and 4.94% from our EPK. And we're just going to add all those together, giving us a total of 59.28% silica in the entire glaze. Now we're just going to go down the line and do this for each individual material. Alumina is 8.84 from nephsi, 0.126 from flint, and 3.55 from the EPK. Okay, just keep chugging down the line. And now sodium is only coming in from nephsi. It's 4.12%. So we have 4.12% sodium. Okay, makes sense. Even if it's simple, it's just fine. And then we're just going to go ahead and fill in the rest of the numbers here, and you can track my math. I'm pretty sure it's good. So now we have this column, the sum of the oxides, and this is the total amount of each individual oxide in the glaze as a whole. Okay, on to the next step. We need to convert to moles, and the formula for that is weight divided by molecular weight. And the weight is the number we just calculated, the sum of the oxides, and the molecular weight is the number I referenced previously. Again, silica is 60.09. So the first number is 59.28 divided by 60.09 equals 0.99. Okay? Makes sense. This is giving us the number of moles, and moles is just a way of looking at atoms in proportion because each atom weighs something different than each and every other atom, and we need to look at our chemistry in an atom to atom basis because that's the way that chemistry works. So we're just putting everything into a molecular proportion. So 59.28 divided by 60.09 is 0.99, and we move on. Alumina is 12.52 divided by 101.96 equals 0.12. Okay, and then we move on. Sodium is 4.12 divided by the molecular weight of sodium, which is 61.98, and we get 0.007. And again, we're just going to fill in the rest of the math to save us on time. But again, the math all checks out. Okay, we're almost done. 2 more steps. The next step is we need to sum the fluxes. Now, if you go back and watch our other videos, like why are cone temperatures random, or our workshop, Glazed to Confused, Understanding the UMF, you'll understand that we're putting everything in proportion to the fluxes. We are now making our 1 gallon of gas. Okay, and to do this, we take everything that is a flux, and that could be lithium, sodium, potassium, magnesium, calcium, strontium, barium, or zinc. Now, in this case, we've only got sodium, potassium, magnesium, calcium, and that's fine. As long as it's in that list, we're going to take it. We're going to take all the numbers that compose that system, and we're going to add them together. We're going to sum the fluxes. So when we take this group, we've got 0.07 plus 0.02 plus 0.001, which is still within our significant figures. It's the smallest it can be, but it's still there at this point, and 0.2 calcium. We add them all together, and we get 0.291. So that is the sum of our fluxes. Okay, ready? Here's the last step. We divide each and every molecule by the sum of the fluxes, including the fluxes themselves, and that's important. So we start off with silica. 0.99 divided by 0.291 equals 3.4. Move on to alumina. 0.12 divided by 0.291 equals 0.41. Move on to sodium. 0.07 divided by 0.291 equals 0.24. Okay? And we're going to go ahead and fill out the rest. Okay, so now our potassium is 0.07, our magnesium is now 0 because when we divide it, we get a very small significant figure. So we've now rounded out to 0 on this material. We're just going to say it's 0 at this point, which is fine. It's a rounding error, and again, if you're doing this on software, you're not going to get this. You'll get a very accurate specific number, but for us, it's okay to round it out for just this example of doing it by hand. Calcium is 0.69, iron is 0.003, and titanium is 0.003. And iron and titanium are just color and contaminants. At the end of the day, they don't play a role in our glaze, but they can affect the color because they're there. But these are exceptionally small amounts. Okay, so we now have these numbers. Great. You got a bunch of numbers. Congratulations. So what? So what is actually exceptionally important because these numbers mean a lot, okay? They tell us exactly what this glaze is going to do and how it's going to function. There is a secret language hidden inside these numbers, and it is your skill to learn how to read the secret language. And the key to this language is this map right here. This is a map that was developed by a man named R.T. Stahl in 1912. And very simply, every glaze that exists on this map. Okay, and it's a mind blower. Basically, we've got silica across the bottom and we've got alumina across the top. And the other thing is that we've got our set fluxes, which again, I'm not going to go into here, but go back to why are cone temperatures random or glazed and confused, and you'll understand what I'm talking about. But we've got our 0.3 to 0.7 flux ratio, which is radically important. So every glaze on here has exactly the same 1 gallon of gas, the same 1 mole of fluxes, and we increase silica and alumina in proportion to that. Okay, and that's rather important. So let's take our glaze and see where it falls on the map. Now, the first thing to do is to make sure our fluxes are in line. And to do this, we need to look at our alkaline metals, which are lithium, sodium, and potassium. So in this case, we've got sodium and potassium at 0.24 and 0.007. When we add them together, they equal 0.31. Great, that's right in line with the potassium on the standard. We're 0.01 off, which is nothing. So by default, our calcium comes out at 0.69, which again is 0.01 off from the standard. Perfect. This glaze is already beautiful. We're meeting the standard for our UMF numbers, which means this glaze will perfectly fall on this map, and 0.31 plus 0.69 equals 1, our 1 gallon of gas, and that's the whole basis behind the UMF. Now the next question is, what is this glaze going to look like? And the cool thing about the map is there's a whole bunch of regions in here. And the first one to note is right through the middle, you've got these two lines and it says bright. Okay, and bright means glossy. Like I said, this was written in 1912, so their language was slightly different. But there's bright, there's semi-matte, there's unfused, and there's devitrified. But basically what we want to see is where this UMF number and where this map predict our glaze is going to be. So we have 3.4 silica, we have 0.41 alumina, and on the map, they fall right there. Right here in the middle. Here's 0.34 silica, and here's 0.4 alumina, and we move right over, and there it is, right in the middle of our bright, glossy cone 10 region. And shockingly enough, when we look at our glaze, what is it? It's a cone 10 gloss. Exactly what the map says it will be. Like, this should be melting your brain right now because this is so incredible, because glaze behavior is predictable. Every time we can know why glazes do what they do, why they're not doing what they should be doing, what's wrong with glazes, how they work, and how they don't work. This is a game changer. This is the system that allows you to take your glaze and take control of it, to own color, to own texture, to own glaze flaws, because the secrets hidden in this map will change your studio forever. The UMF is by far the most powerful tool that the ceramicist has to take control of their aesthetic and technical challenges. because you now own your glazes. There is no magic in spirit of the fire. There is chemistry that you can become the master of. And that is the most powerful thing you can do to make your studio the best it can be. So if you want to learn more, please come over to ceramicmaterialsworkshop.com and take our first online workshop, Glazed and Confused, Understanding the UMF. In just a couple hours, we will change your studio forever, and you will start to understand and take control of your glazes. We will take a deep dive into what this UMF thing is and how it works, how we read it, and what we can learn and what we can do with our glazes from the UMF. It's incredible, and it's available now at ceramicmaterialsworkshop.com for only $10. And if you're a newbie and you made it all the way through this video, congratulations, kudos, go watch it again. Coming out soon will be our next online workshop, Glaze of Our Lives, Understanding Glazes for the absolute beginner. If it's all confusing to you, we will walk you through it to make you take control of your glazes. So come on over to ceramicmaterialsworkshop.com. It's a place online to learn and discuss ceramic materials and learn everything you want to know about materials, firing, and process. If you want to begin to learn but don't know where to start, if books have left you cold, if your teachers just keep repeating the same thing, if you need to know how clay and glazes work, if you want to know why firing temperatures work, why cone 10, why cone 6, why cone 04, if you want to improve the safety and durability of your glazes, if you just want to have the coolest glazes on the block, or if you just need to know more, come to ceramicmaterialsworkshop.com and you can come participate in the conversation. If you have a question you'd like for me to address in one of my Everything You Want to Know About Clay and Glazes but Didn't Know Who to Ask series, email me at matt@ceramicmaterialsworkshop.com, and please consider supporting us on Patreon or PayPal. The links are down below, and that helps the content keep coming so we can keep getting you informed and educated and make you the master of your studio. So thanks, and I hope to see you over at ceramicmaterialsworkshop.com.